This is video number 9 in our series Topics in Tensor Analysis. We left off in the previous video with this expression. Uj is one of the curvilinear coordinate axes, and we just sort of took that symbol for it and plugged it in to when you're taking a gradient of a scalar. We said, let's just go ahead and follow the formula, and we would get the partial of uj with respect to x1 times the unit vector for the x1 axis plus the partial of uj with respect to x2 times the coordinate vector for the x2 axis, and finally the partial of uj with respect to x3 times the coordinate vector for the x3 axis. So we have the generalized curvilinear system, u1, u2, u3, and then here we have the Cartesian axis here, x1, x2, and x3. And as we explained in the previous video, we assume that we know how to transform from the u coordinates to the x coordinates and vice versa. That's what this means. So, for example, u1, that would be some function of x1, x2, and x3. u2 is a different function of x1, x2, and x3. u3 is yet a different function of x1, x2, and x3. And in the previous videos, we used spherical coordinates to show specifically how that would work, where we have the spherical coordinates r, theta, psi, where r is the magnitude of the position vector, and then we have theta and psi. And here's our Cartesian coordinates. We know how to transform from spherical coordinates to Cartesian coordinates and vice versa. That is given by these set of equations here, where if we know what the spherical coordinates are, then we can determine what the Cartesian coordinates are. Each one is a different function of the spherical coordinates. Or, conversely, if we know what the Cartesian coordinates are, each spherical coordinate is a different function of the Cartesian coordinates. So here, this is taking the exact same concept, only we're generalizing it to our system here. So we're saying we know that u1 is some function of x1, x2, and x3. Same thing for u2, same thing for u3. So I can certainly take the partial of this with respect to x1. I can take the partial of this with respect to x2. I can take the partial of this with respect to x3. I can do that for any one of these. And that is what this expression here is about. I can take the partial expression of any one of the curvilinear coordinates. Let's just say j equals 1. So the partial of u1 with respect to x1 times the unit vector for that axis, plus the partial of u1 with respect to x2 times the unit vector for that axis, plus the partial of u1 with respect to x3 times the coordinate vector for that axis, for the x3 axis. And we can do this when j equals 1, j equals 2, j equals 3. And again, to give us a specific example, let's take the spherical coordinates, where here one of the spherical coordinates is the magnitude of the position vector. And this is how it's expressed in terms of the Cartesian coordinates. So we can take the partial of this, but note here, with respect to x1, and multiply it by the unit vector for that axis, plus the partial of the same expression with respect to x2, multiplied by the unit vector for that axis, plus the partial of this with respect to x3 times that unit vector. Or we could take the angle psi this is how we express it in terms of the Cartesian coordinates. And we can take the partial of this with respect to x1 times that unit vector, plus the partial of this with respect to x2 times that unit vector. And we can write the expression here for x3, but of course this is going to be 0. There is no x3 in here, so that's just 0. But the point is that when we know these transformation equations, then we can take these types of derivatives with no problems. And we can do that for each one of the curvilinear axes. So by doing that, that gives us a vector. And that's a gradient type vector, because that's how we obtained it, was using the gradient formula. Now, before, what we were doing was taking the partial derivative of the position vector with respect to any one of the curvilinear axes, and that gave us those tangential vectors that we talked about in the previous video. What kind of a vector is this? Well, we'll give it a label. Unlike the tangential vectors, we'll put the label upstairs. Okay, but still we don't know much about what this means physically. So let's do this. Let's take the dot product of the tangential vector, EI, that's this, and let's take the dot product of it with this new vector, this new kind of vector that we just created that we're labeling like this. So that means we're taking the dot product of this with this. So here, that's going to be 1. All the other expressions will be 0. So that's going to give us this component times this component. And then we'll have this times this. That will be 1. And we're going to have this component times this component. And then this dot this will be 1. So now we're going to have this component times this component. So when we take the dot product of this, we get this kind of expression then. We have EI dot EJ, and that equals a partial of x1 with respect to UI. Then we have the partial of uj with respect to x1 plus the partial of x2 with respect to UI. Then we have the partial of uj with respect to x2. And then we have the partial of x3 with respect to UI. And then we have the partial of uj with respect to x3. And again, these three terms just simply come from this times this plus this times this plus this term times this term gives us this expression. And of course, looking at these in terms of the chain rule, this just gives us notice we write it like this, and this is EI. I'm not going to put the bars on these anymore. Dot EJ. We did not put the 3 there. There's not 3 of them. There's only 1 of them. And the reason for that is, let's just consider a differential in general. We have this is equal to, I'll make this a general expression, say dw. That's equal to the partial of w with respect to x1 dx1 plus the partial of w with respect to x2 dx2 plus the partial of w with respect to x3 dx3. So this is part of the differential of dw, this is another part, and this is a different part. So if we divide this by dw, well, this is 1, and this is 1, this is 1, and this is 1, but this is equal to 1, not 3. And the reason is we're adding partials together here to get the entire component. So, and that same rule applies here. So this is equal to this expression. Now, let's see what this means. In fact, let's just write it over. We have that this is a tangential vector dot the new kind of vector we just made, and we said that is equal to the partial of uj with respect to ui. Now, if j equals I, then we just have the partial of ui with respect to ui, and then we have ei dot ej equals 1. Now what happens if, though, j does not equal I? They're different. For example, what would happen if we took the partial of u2 with respect to u3? So here we have the partial of u2 with respect to u3. Well, these coordinate axes are completely independent of each other. There is no equation that relates this axis to this axis, just like there is no equation that turns this axis into this axis, or this axis plus this one equals that one. There is no equation that does that. These are all independent axes, and the same thing for these. So this equals 0. So here then, if j does not equal I, then we have that ei dot ej equals 0. So we can express this like this, saying that ei dot ej equals the Kronecker delta. Then you write it like this, ij. Now you probably have seen the Kronecker delta written before, where it's like this. We'd have ij, where that equals 1 when I equals j, and that equals 0 when I does not equal j. But now we're in the situation where we have subscripts and superscripts, so we write it like this. But that means then that this equals 1 when I and j are the same, otherwise it equals 0. So the dot product of these two, if it's ei dot ei, is just 1. If it's ei dot a different one, this lower one, dot ej for a different number here, if this was e1 dot e2, that equals 0. So that means that these are orthogonal. So, and remember how we got these. Let's just make some room here. ei, that was our tangential vector, And that was obtained by taking the partial of r with respect to ui, and then this we got by taking the gradient like this of uj. So these then are all orthogonal to each other. Unless j happens to equal I, then that equals 1. So these form what are called a reciprocal set of vectors then. Now, that came from considering this generalized curvilinear system here with u1, u2, and u3 coordinate axes. We just have 3 of them here. Of course, the same rules apply regardless of how many number of coordinates that we have. What we want to point out is if you're dealing with, say, a system like spherical coordinates, where here all of the different axis components, they are all mutually orthogonal to one another, then if I take this or if I take this, it gives me the same thing either way. In other words, if the curvilinear systems are already orthogonal to one another, then this will give us a set of vectors, this will give us another set of vectors, but actually if you go and take those derivatives and compare it with these, they come out to be the same. We're not going to show that in this video. So what we mean then is that when we have curvilinear coordinates that are not mutually orthogonal, and we have a tangential vector, and then we had the gradient type vector that we created, that we just demonstrated, then these are orthogonal to one another. So we get this general expression. This is EI dot EJ. So these are what we call reciprocal vectors. And we had to go through this whole discussion here because several times now in the previous videos we said, well, suppose that we have these types of a curvilinear system like this, and we just considered the u2 and the u5 coordinates here, and we have a vector A, and we said, okay, we can express vector A by taking its components along either one of these, along both of these coordinates here, and expressing it like this. Then we said there's something else that we can do. Instead of having u2 and taking a tangential vector, e2, instead, what would happen if we made an orthogonal vector like this? And same thing here for u5, instead of having a tangential vector at that point, what would happen is if we had an orthogonal vector instead. And we can obtain those orthogonal vectors by doing what we just did right here. That's what this turned out to be. This will give us the orthogonal vectors to the tangential vectors. So, and those we label like this. This would be E2, and this would be E5. Where these then, these are orthogonal to each other, and these are orthogonal to each other. Then, if we wanted to, we could express the vector A in a different way with respect to these orthogonal vectors that we just made. So now we say A can be expressed like this. The new orthogonal vector we express like this, so now we write the component with a subscript. and likewise like this. So this is how the vector A could be expressed in terms of these orthogonal vectors that we created. And as we'll show in the next video, this then is the fundamental definition for covariant components of a vector. This, of course, as we discussed in the previous videos, is the fundamental definition for the contravariant components of a vector. In contravariant case, we're taking the components of it along the coordinate axis with their tangential vectors. In the contravariant case, we're taking the components of it along these new orthogonal vectors that we created and writing it like this. Either way is a valid expression. So what I want to show in the next video is that indeed, when we express the vector like this, it will transform as a covariant vector consistent with the way we set it up in the previous videos. And that's what we'll demonstrate in the next video. So come back, join us for that video, and we'll show that indeed this is the fundamental definition for a covariant vector. So come back, join us for that video. We can wrap up our discussion with covariant and contravariant components of vectors and tensors, and then that will set us up to be able to discuss the metric tensor.